So in the previous video we have came all the way to diagonalizing the Hamiltonian. So we got something like this. The h dash, which was the diagonal form of the Hamiltonian, could be calculated by transforming the original Hamiltonian using the matrix S, which contains the eigenvectors of the Hamiltonian. Now, why were we actually doing this at all? So we have set ourselves a few tasks, like a list of steps that we will have to follow in order to solve Schrödinger equation, and this was the step number 1. Now we go to look at the step number 2, which was to solve in this particular basis, solve the equations of motion by finding evolution operator. We will actually define evolution operator in here. Alright, so to solve Schrödinger equation in this particular basis, in the diagonal basis, is actually very simple. So I will write the Schrödinger equation here, and now I will write everything primed here or dashed, because I will assume that we are already in the eigenbasis. Well, we can only be in the eigenbasis if we use the proper representation, which means if we multiply this thing from the left by the proper vectors. Alright, so if we do that, what happens? The equation will turn into an equation for the expansion coefficients. So this a psi dash, that's c a, and it's time dependent, so that's a coefficient. This is a definition basically, a coefficient of the expansion or of the representation of the state vector in a particular basis formed by the vectors a. This means of course many vectors, and the equation for CAT looks the following way. He will make it a little bit more explicit. So A goes to meet H, but there is also H psi dash here. Now we would introduce inside here the unity again in form of the sum over all A's, or well, to use a different index, of all B's. But because H is diagonal, nothing else than just the AA is left out of this. So this is under the condition that we are in here in this diagonal basis. This corresponds to just AA, and we get minus I divided by H bar A, and here therefore we get CAT again, because it's the A psi dash. Now this is of course the epsilon A tilde, the diagonal, the eigenvalue of this matrix, and solution of all the equations with it. So we will have basically, we will be listing through all these A's. For each of them we will write one simple equation like this, and each of these equations has a simple solution. CAT is equal to e to the power of minus I divided by H bar epsilon A tilde t, and multiplied by the initial value of that coefficient. So this is, well, this is all there is to solve Schrödinger equation in the representation in which the Hamiltonian is diagonal. Now the solution, that is our psi dash, can be written as a vector, or it is the vector of these coefficients, and I'm not limiting myself to any particular particular number of states, so it can be any number of states. The initial condition, that means psi, so this is sort of psi t, this is psi in 0, is given by the same vector of the coefficients in 0. So these are the constants that I need to put into the problem to, well, to specify the initial condition. Now this can be written I mean, you see that all these coefficients here, they are basically just multiplied by something. So how do I multiply each element of a vector by different number? Well, by multiplying by a diagonal matrix. So I can write this result in the following way. It's psi prime or psi dash t equals to a matrix which has on its diagonal elements all these guys here, minus I divided by h bar epsilon 1 tilde t e to the minus I divided by h bar epsilon 2 tilde t, etc., and everywhere else 0. And this here I multiply this by c1 0, c2 0, etc. Well, so what I did was to write everything in forms of a certain operator. So let's write this psi t again. There is an operator here which depends on t. I'll call it u t, and because we are again in this diagonal representation, so I'll put the dash here. So it's u t dash, and here it multiplies the vector psi dash at the beginning of time. So this is the solution. I have written the solution in terms of an operator which multiplies the initial vector, and that operator is now called it's called evolution operator. If I add something very little to it, I can call it a Green's function, a time-dependent Green's function also. But that's you know, let's not go into Green's functions yet. So this means, just to summarize, this means that if I get the problem like this in Schrödinger equation, well then, at least in our diagonal representation, I can write its solution very simply using certain operator. Now, what about in general case? How is it in the general case? Well, in general case, I can use this interesting matrix transformation that we have seen in the part 1. So, all right, I will use matrix transformations. I want to turn my problem, which I have specified here. This is where I can solve it. Whenever everything is diagonal, I can solve it. So I have a different, more general problem where I don't have this prime saying that everything is diagonal, but maybe I can turn it into diagonal without changing anything on the problem itself. So this is the initial condition here. Now I will multiply this by density by the matrix S. So multiply, I mean everything, by S, actually S inverse. So in case of multiplication with S inverse, the equations look somewhat the same. So I multiply from the left like this. So here I would have Hamiltonian again, and here I'm supposed to write the S, but well, the equation is not not as psi. The equation is not an equation for psi, but for psi minus 1 psi. So S to the power of minus 1 psi. So what I would like to do here would be to introduce another version of my beloved trick with the unity. I introduce 1, there is a space here, so nothing, 1 in a form of S to the power of minus 1 and psi. So this changed nothing because this is still 1, but I have got my equation again with the same equation on the left and right hand side of the equation. And here to my pleasant surprise, there is this s to the power of minus 1 hs, which is my diagonalized Hamiltonian. So here I have h prime, my diagonalized Hamiltonian, and this would be the psi prime. So this is psi prime. All right. It seems like I have now been able to solve the whole problem, or basically to at least I have been able to turn my original equation completely into the form where I know how to solve it. And the question will be now whether I can also perform the transformation back. For that we will have a, one has to do something more about this one. So we know that the U is built as a matrix with all these eigenvalues on the diagonal, e to the power of the eigenvalue, etc. So that corresponds to a matrix version of, let's say, of exponent of a matrix. So exp minus I divided by h bar s minus 1 hs, that is the u prime, that is the one which we defined in the diagonal basis, and that one solves this problem. And that's the problem in the original basis. But how do we turn it to the that's not the original, it's the diagonal basis. How do we turn it to the original basis? So from here we can go to the original basis by multiplying everything by the inverse of this, that is by s. Yeah, if I multiply now this whole thing by s, I'm going to get back the psi, because s multiplied by s minus 1 gives 1. So here I get the s psi t, which actually equals the psi t, that equals s u dash t, and here I would be writing psi dash again, but I can again use the s minus 1 s psi dash, which will give me here the psi. And that looks like I found what I needed. I can now say that ut now without dash is actually s u dash t s to the power of minus 1, and I can write it even more explicitly now using this definition. It's then s exponent of minus I divided by h s minus 1 hs, and here s to the power of minus 1. So that's my evolution operator, the thing that is able to propagate the vector, the state vector, from its initial value to the value at time t, and all that is now in the original basis. The only thing that I need to find out now is if this really works. I mean, if I take this definition and put it into the original Schrödinger equation, if I really get a solution of that original Schrödinger equation. So let's do that as the last thing, basically. So I want to prove now that the following thing, that psi t defined in this way, well, write it as an abbreviation like this, solves the Schrödinger equation. That is, when I send on it this time derivative, that is, I send time derivative of on this, that it gives me back the same equation. So alright, by definition this is now, so I write the s, which is constant, nothing is changing here. The only thing that the derivative touches, and I'm sorry here for a big mistake, here is t as time, here is also t as time, and maybe I didn't lose it anywhere else. So there is a t here, so if I take a time derivative, the property of exponential is such that everything in front of the time derivative goes down here. So I get minus I divided by h bar s minus 1 hs closing, and here is the function again. Now if you wonder, for example, what is the definition of the exponential thing of a exponential function of a matrix, then well, the way that we got to it here is basically the way it is defined. If I have any function of a matrix, the rule of thumb is I first diagonalize that matrix, then I define the function by basically using it just on the diagonal elements, and then I convert it back by transformation back to the original basis. That's how you even define this thing, this function of a matrix. Another way to do this would be to define the function by a series, power series, and the same power series, if you repeat with matrix, you also get the proper definition of a function. Alright, so the last thing to do here is this s minus 1, and now you see, well, the whole trick is that this kills with this, and from here to here it's the u. Okay, I forgot one thing that is sitting up here, that's the initial condition, and this is u multiplied by the initial condition, and in front of that I see just minus I divided by h bar multiplied by h. So that is the Schrödinger equation. We got back the Schrödinger equation, psi t equals minus I divided by h bar h psi t. So this wave function defined by this operator, to which we got by basically transforming twice certain matrix, really solves the equation of motion. And in our little program, in our little scripts, what we will do will be as precisely as described in this third step. So from somewhere we would have to actually say, well, this is from here, it's at 3. So in our little programs, what we'll do, we'll find this matrix for a little time step dt or delta t, and then we propagate iteratively our wave function from the initial value. So we will have initial value for our state vector. I multiply it by u delta t, which gives me psi at delta t. Now I multiply it again by delta t, which takes me from time delta t to time 2 delta t, etc., etc. In this case, I mean, there are, well, in this particular case, actually, the evolution operator for, I mean, properly one would have to say this is an evolution operator from some t0 to t, but it only depends on the difference of the times. Actually, you see here, you can really put anything. That's the distance in time you travel. T is the distance in time you travel. So in this way, we can solve Schrödinger equation iteratively by calculating this matrix once. And that matrix, once you set the delta t fixed, is a constant matrix, and you can multiply again and again your state vector and propagate it by this delta t into the future. So this is what we will do. For that, we will need a little bit more knowledge slight knowledge of programming. So in another video, I will discuss how to use Octave to turn all these theoretical calculations in here into practical calculations with matrices.